I'm Meghamala from Electronics and Communication Department, working as Assistant Professor, Institute of Aeronautical Engineering. So, coming to today's presentation, and today's topic is all about time delays with switch primitives. So, as we discussed in the earlier classes, in the Verilog library, we have 26 sets of primitives. 26 sets of logic primitives we have in the Verilog. So, these primitives, it could be of gate primitives or else it could be of different operator primitives, whatever. So, here coming to the time delays in switch primitives is a main topic of today, and let me talk about some delays. What is a delay? Let us recapitulate regarding the delay word. So, delay is nothing but it is a term with respect to a time. So, it is all about concern with respect to the time constraint. So, with how much of amount of the propagation of wave taking place with respect to the input and as well as with the output. So, here coming to the delays, we have different types of delays. Event delays, time delays, process delays and so on. So, when it comes to the time delays, for example, let us consider a module. This module, it could be a combinational circuit or a sequential circuit, whatever it is. So, this combinational or a sequential circuit, for example, let us consider a gate, a normal gate, AND gate. So, for this AND gate, we have two inputs A and B and the output. We all know the mechanism of how this AND gate performs. That is Y is equals to A dot B. Isn't it? So, the truth table follows like this. 0, 0, 0, 1, 1, 0 and 1, 1. For this, the output goes 0, 0, 0 and 1. Isn't it? So, what happens when the propagation takes place with respect to the inputs, two inputs A and B? Sometimes what happens is, if the input, if I am propagating or else if a variable A is taking its position with the delay of 10 nanoseconds and B is taking with respect to one more 10 nanoseconds. So, at the output, this is all about the input, but at the output, what should I observe? I must observe that the input is taking, one of the input is taking its propagation at 10 nanoseconds of delay. So, I have to observe the same 10 nanoseconds of delay at the output. Isn't it? So, likewise, B also, it's take the same time. But in some cases, what happens is, due to some disturbances or else due to some chaos which is happening in between the module here. So, what happens is, the delay, it may lead or it may lag. Maximum cases we see the delay would be lagging, isn't it? That means what? Instead of obtaining a 10 nanoseconds of delay, we may see 30 nanoseconds or 50 nanoseconds of delay due to the chaos or else due to the disturbances that is interfering in the module. Okay. So, this is nothing but the time delays. So, coming to the event delays. What are the event delays? Event delays are also same like a time delays, but here what happens is the events which are taking place with respect to the input, sometimes what happens is we may observe some delays is been occurring due to the eventually the events will be occurring. That means what? Eventually, without unknowingly, sometimes a particular peripheral activities will be involved into the module. So, in such cases, what happens is, in order to obtain a proper output or else in order to obtain the output in a right way, sometimes we may see that, we may observe that the delay would be extended with some nanoseconds, more than what we expect. So, this type of event delays would be occurring when a particular designer is designing some tool, some module, some tool. Okay. So, like that, we'll be seeing some delays. Okay, in whatever the module that you are considering, that you are whatever the module that you are developing, in all the modules, whatever the modules that you are developing, you will see some delays which are occurring with respect to the input and as well as with respect to the output. But all the delays would be in terms of time constraints. Okay, so coming to the time delays here, we all know in the previous classes when we are discussing about the bidirectional gates. Okay, bidirectional gates, we have seen that, we have discussed about there are 6 bidirectional gates. So all 6 bidirectional gates are with respect to tran and rtran. That means what? A normal gate with and also with respect to the resistive switch. A normal switch and as well as with the resistive switch. So such that totally we have 6 bidirectional switches. Tran, rtran, tran if 1, rtran if 1 and tran if 0, rtran if 0. So totally 6 kinds of different bidirectional gates switches we have seen. In such bidirectional gates also there are some delays which are occurring. Okay, so the gates, the delays are with respect to the inputs and as well as with respect to the output. Sometimes the switches that you are considering is a unidirectional switch, then the gate would be observed, the delays would be observed output with respect to the input that you are considering. Sometimes if your switch is a bidirectional switch, and then in that case also as well, we will see some delays as well as with respect to the input and as also with respect to the output. So in all the perspectives, we see the delays or the time delays would be in terms of 3 kinds. That is rise time, fall time and off time. So here we will see there are 3 different types of delays in the Verilog. As we see that Verilog is a very case sensitive language. So in this Verilog, we have a library, Verilog library. In that Verilog library, we have 26 sets of primitives, Verilog primitives we have. So some primitives are with respect to the gates and some primitives are with respect to the switches as well. So here, coming to the switches, the primitives, we have different types of switching primitives we have in the Verilog library. So here, there are different types of Verilog delays in the Verilog. They are, we know this like rise time, fall and the turn off delays. As I said, delays are calculated only in terms of time. So we can call this rise time, rise delay, fall delay and turn off delays as rise time, fall time and as well turn off time. Okay, so these delays, what does they do? They declare, the declaration contains up to 3 values. Okay, so the declaration, wherever you are finding some delays and those delays are with respect to rise time, fall time and turn off time, and if there is any possibility of declaring or initializing these delays, then we can initialize these in terms of 3 times. That is rise delay, fall delay and as well as turn off delays. Okay, so what is this rise delay, fall delay and turn off delay? We will discuss. So coming to the rise delay, the time taken out for the input of a gate to change the values of from value to change from some value to 1 is called the rise delay. That means what? Here this is taking it's telling that the time taken for the output of a gate. So what the time taken for the output of a gate to change its value from value to 1. Okay, that is what something, if it is changing its value from 0 to 1, that is from low to high, then we'll be calling such delays as rise delay. Why? Because here we are seeing the delay is taking rise, right? The delay is eventually rising up from 0 to 1. So as it is taking the value 1, which is high, then we are calling it as, a rise delay. Similarly, when we look into the false delay, we see the time taken for the output of a gate to change its value from 1 to 0. Isn't it? So when the the time is taking its position from 1 to 0, that means what? Which is falling down. So when the time is falling down, obviously we are calling that delay as fall delay. Okay, so this is nothing but the fall delay. And time taken for instant, if it's falling down from high to low, is nothing but the false time. We represent the rise time as TR and false time as TF. And then coming to the turn off delay. What does this turn off delay says? Turn off delay is nothing but the time taken for the output of a gate to change from some value to high impedance. So if it is taking some value, okay, if it is taking from some value, not at the constant, not at the particular limit, but even if it is taking to some constant, then we are calling that delay as turn off delay. So usually we represent the turn off delay in this Verilog as TO. So here the turn off delay is simply to understand is when a particular constraint, if it is not limited to a particular number, and if it is going beyond that number, beyond that number is nothing but to some constant, to some extent, if it is moving on, then we are calling that delays as turn off delay. So here the value which is going to has a high impedance value, okay, to some saturation point, if it is moving on, then we are calling this as turn off delay. So these are the few time delays that you can observe when you are executing a particular program pertaining to the gates, pertaining to the whatever the circuit that you are considering, whatever the digital circuit that you are designing. Okay, then you will be observing some delays, and those delays would be in terms of these three different types: rise time, fall time, and turn off time. That means rise delay, fall delay, and as well turn off delays. So here, if only one delay value is specified, then it is used for all the signal changes. The default delay is 0. So here what happens? Sometimes we see only one delay. Sometimes we will see two delays. Sometimes we see three delays, right? So here when you have only one delay, okay, if we observe only one delay is specified, the value of one delay is specified, then that delay value, it would be used for all the signal changes. Okay, for all the signal changes, the only one delay that we have is sufficient. That means what? It can be signifies. And then the fault delay would be, the default delay would be 0. Why? Because here we have only one delay, right? So obviously the default delay would be 0. Because of this reason, what we are saying is, in the bidirectional switch, we have written delays, 0 delays. How can a instantiation of a particular switch can be written is trans terminal list. In the terminal list, output S1 and S2. This is how we represent when the delays are 0. When the delays are 0, when the delay value is only 1, and that value, that delay value is signifies for all the signal changes. Then we are calling it as a 0. The default delay value would be 0, and the instantiation of that particular 0 valued delay would be written like this. Coming to two delays. If you have any two delays that are specified, okay, if two delays are specified, then the first delay specifies a rise delay and the second delay specifies the false delay. So here what happens, if you find any two values, okay, two delays. So in the two delays, first one is, for example, let's say 0 and 1. These two are the delays that we have observed. So here in this particular two delays, we can specify that one particular delay as rise delay and the other particular delay as false delay. Okay, so one particular delay as rise delay and the other particular delay as false delay. If and only if you have only any two delays that are specified. If you have two delays that are specified, then you can specify one delay as rise delay and the second delay as a false delay. Okay, we know the representation of rise delay as TR and the representation of false delay as TF. Then, if the signal changes to high impedance value or unknown value, high impedance or unknown value, then the similar value would be termed as turn off delay. Okay, delay turn off delay. So here we can see these are the relays, right? Turn off delay, rise delay, false delay, and as well as turn off delay. So when we are calling it as a turn off delay, when the signal changes its value to a high impedance value or else an unknown value, isn't it? So here we see if the value if it is changing not to a particular limit. Okay, if the value changes not to a particular limit, but if it is changing beyond the limit, that means it may go at high impedance or else sometimes it may go as an unknown number. Then that delay would consider as turn off delay. Then the delay would be considered as turn off delay. So here how this is just a representation of a delay. If it is one delay, then the signal by default the delay of that particular signal would be 0. Okay, then there is no need to represent any delays in the instantiation. But if you have any two delays which are specified, then we can represent one delay as rise delay and the other delay as the false delay. And here one more case is turn off delays, where here turn off delay says that when the signal is going beyond the limit number, when the signal is passing beyond the limit number, it may goes to high impedance or else sometimes it may goes to an unknown number. Then such cases or such delays we can call as turn off delays. And usually we represent turn off delay as TO. Okay, rise delay as TR, false delay as TF, and turn off delay as TO. And see, this is how the representation, the graph says that. See here, we have, it could be either 0, it could be either X, or it could be either Z or 1. That means what? Either if it is from 0 to 1, or from 1 to 0, or sometimes from 0 to Z, 0 to X, or else 1 to X or 1 to Z, isn't it? So for rise time, how we are saying it's a rise time? Why? Because here you can see from it is taking, the propagation takes from 0 to 1, isn't it? It is rising up, right? So as it is a rising up, then we are calling it a rise time. And for the fall time, it's similar, says that if it is from 1 to 0, from high to low, from top to bottom, that is from high level, that is 1 is a high level, isn't it? So from high to low, if it is falling down, when it is falling down from high to low, then we are calling it as a fall time, TF. The delay is considered here as fall delay. Okay, delay, delay, fall delay. And then coming to the turn off time. What is this turn off time is? I said you when the value beyond the limit number. Okay, when the value, the process it goes beyond the limit number, it may goes to high impedance or else the unknown value, isn't it? So here from 0x or x to z. That means what? See, it's a constant and then it's going down at some value, and also it is falling actually. And when it comes to the second one, it is 0, constant, and it's going to high. So it is rising, isn't it? So it is rising beyond the number and it is falling beyond the number. So that beyond numbers, it would be z or some unknown values, obviously. So such kind of delays, we are calling it as a turn off time, isn't it? At this turn off time, what happens is both the signals are in the 0 condition. Okay, signal 1 and signal 2, they can't go beyond the time, right? So obviously the switch will be in the off state. This is what you have to remember when it comes to the rise time, fall time, and turn off time. So we'll see if three values are given. Sometimes if three values are given, then the first value specifies a rise delay, and the second value it specifies a false delay, and the third value specifies the turn off delay, rise delay, fall delay, and turn off delay. So as we discussed in the previous slide, we said that sometimes we represent only one delay, isn't it? We represent only one delay. Sometimes we represent two delays. Sometimes we represent three delays. So pertaining to one delay says that if there is no delay, though the wave has been propagated from the input to the output as well, but without any delays, when the delay is 0, isn't it? Then delay value would be 0 obviously. So there is no need to represent the particular delay value, isn't it? So this delay is nothing but the one delay. So coming to the two delays, in the two delays there is a representation of, for example, 10 nanoseconds and 20 nanoseconds of delays time. So what does this 10 nanoseconds and 20 nanoseconds? We can consider for this 20 nanoseconds and 10 nanoseconds, isn't it? So for this 20 nanoseconds, I can consider one of the time delay is a rise time and one of the time delay is a false time. This is how being a designer can represent or else can consider the delays. One as a rise delay, another as a false delay. Why? Because here I have two delays, right? So I can consider that one as a false delay and one as a rise delay. And for suppose if these delays are, if there are three delays, sometimes what happens? I have 10 nanoseconds, 20 nanoseconds and 0 nanoseconds. So here in this case what happens is, being a designer, I can consider one among three delays. One delay I can consider as a rise delay. One more delay I can consider as a false delay, and another delay I can consider as a turn off delays. Okay, so these three are the representations. In some cases you may observe only a delay without any delays, and in some cases you may observe with two delays, and in some cases you may observe with the three delays. Being a designer, you have to analyze that if it is two delays, one can be a rise time and there can be a false time. If it is a three delays, one can be rise time, another can be false time, and the third one it would be a turn off time. Okay, so if the signal changes to an unknown value, then the smallest of these values will be used. So here this sentence is talking about a Z or X values, unknown values or high impedance values. We say that turn off time is nothing but a high impedance values which is going beyond the numbers, beyond the limit. If a signal is passing beyond the limit, that means what? See here, if it is, this is a false time, right? See, this is a false time. This is a rise time. So this is an extent. Beyond that extent, if a signal is still passing on, then we will be calling that values. Okay, so the signal which is passing through these values are nothing but the unknown values. And as well, in the falling cases as well, in the falling cases, it has to fall from 1 to 0. And beyond that, if the signal is passing on, it may goes to another unknown values, okay, which are not needed. So we can represent the high impedance values or unknown values. So these are nothing but the unknown values, and these are nothing but the high impedance value. So these values can be omitted. That means what? Here in such cases we can't see any delay. The switch will be off. The switch, whatever the switch that you are considering, though it is pre-transistor, NMOS transistor, PMOS transistor or CMOS transistor, whatever the switch is considering the delay as turn off delays, then the delays would be, then the switch would goes to the off condition. So here the signal changes to unknown value, that is Z or X. Then the smallest three of these values will be used. So here, for example, this is to this extent, my value is, for example, 0.09, and beyond that it's going as 0.001, 0.002 like that. So what happens? Till this extent only I can consider my turn off time. My turn off time would be 0.09. That's it. So beyond this I cannot take the values. Why? Because here the switch, the mechanism of the switch goes to off. So here to only this value as turn off, the value of time delay as turn off time delay would be considered only to this value, that is 0.09 can be considered. Beyond that it won't be considered. So these delay apply to any signals as they all can rise or fall anytime in real circuits and not restricted to only output of gates. So here this sentence is telling that the delay is applying to any signal. Okay, so for any kind of signal, for any sort of input that you are applying any delay, so this delay can the delay values, it could be a rise or fall. Okay, only the time delays, such kind of delays we can see only in the real time circuits. and also the values which can be applied to a circle can be seen in the real circuits, and they are not restricted to only output of the gate. So whatever the delays that you are giving, the values that are specifying with respect to the rise time, fall time and turn off time, they are not only restricted to be given at the output, but also they can be given at the input as well. Being a designer, I can give my delay values. In order to know the signal strength of a particular signal, I can give the delay values to the inputs. Okay, this is what the sentence states. And so here, there are three ways to represent gate delays. So here, as we are discussing the gate delays, these gate delays can be represented in three types. Okay, in three ways we can represent the gate delays. The first one is one delay format. The second one is two delay format, and third one is three delay format. So here we have discussed, right, previously, the three values. The values can be given for three different values. That is one delay, two delay, and three delay as well. So we'll see the two delay format can be applied. See, the two delay format can be applied to most primitives whose output does not transition to high impedance. So here we are saying that a two delay format. Two delay format is nothing but, for example, I've considered, right, delay 20 nanoseconds and delay 10 nanoseconds. So these two delays I can give to the output, any of the output. It means that the values are beyond the limit, not the values are within the limit, not beyond the limit. So that's the reason I can give, I can say one of the time as rise time and one of the time as the false time. But in some cases, like in some cases, what happens is the signal may rise, it may shoot up. Okay, it may shoot up to some extent where the values are disabled. So such values are called the unknown values, and such kind of values we can say as a high impedance values. So we cannot consider such high impedance values. We can only consider only the within the limit if the signal is taking its propagation only within the limits. Next, this is a two delay. Then coming to the three delay. A three delay format cannot be applied to an AND gate because the output will not go to Z for any input combination. Isn't it? So as we are considering here an AND gate, it is saying that A, B and Y. So here for this AND gate, we can consider a delay of 1 bit delay and 2 delay. 1 delay and 2 delay. But we cannot go for 3 delay. Why? Because here in this AND gate, we cannot see, there is no possibility of observing any value in terms of high impedance and as well in terms of unknown values. Isn't it? Gate is a very simple circuit, very simple logic circuit where you can analyze the mechanism of how it works. Isn't it? So here in the AND gate, we cannot see any high impedance values or unknown values regards to this AND gate. But other combinational circuits, other complex circuits that you are designing, being a designer, we can design many complex circuits, right? So in such many complex circuits, if there is a possibility of observing 3 delays, okay, there's a possibility of observing 3 delays, 2 delays and 1 delay. But as of now, as we are considering AND gate as a simple simple circuit, we are saying that in this particular example, we cannot see, there is no chance of observing any high impedance value and as well as the unknown value, as Z value and as well as the X value, unknown value, high impedance value. So the AND gate, we cannot see we cannot consider the 3 delay format. Only that we can consider is 1 delay format or as well 2 delay format. But for the complex designing, we can go for the 3 delay format. Why? Because we have in the 3 delay format, we'll be having the rise time, fall time and as well as the turn off time. And now single delay specified. So here, how a single delay specification takes place. This single delay, it is used for all 3 types of transition delay. That is, say here only we have delay, right? 1 delay. with the name of the circuit that you are considering, and this is the terminal list, isn't it? So the terminal list consists of output and as well as input, and it is the name of a gate, and here only one delay, single delay. If you are observing any single delay in a particular circuit that you are considering, then this is how the initialization takes place. And then goes for the two delays. Two delays specified used for rise and fall transition. So as we discussed, for the two delays, being a designer, if you want to just propagate any two delay, if you want to give us specify some values, okay, if it is a two delay value, then remember that one value it could be we can give as for the rise time, and the other value we can give for the false time. So this is how it takes place. Two delay specified, that is used for rise and fall transitions. Okay, so how can we specify is, see, this is a rise time and this is a fall time. This is the name of a gate and terminal list. And then three delay specification. So in the previous example, we have considered a simple gate, AND gate. So for that AND gate, we may go for the single delay and as well two delay, but we cannot go for the three delay. Okay, but when it comes to when you find somewhere to give a three delay specification, then how can we give is rise time TR, false time TF, and turn off time TO. This is the name of the gate, and here is a terminal list. So this is how the specification of one delay, single delay, double delay, and triple delay, three delay specifications, two delay specifications, and as well as the one delay specifications takes place. This is how we can write the initialization of the delays. So we'll discuss what is a one delay format. So when you are designing some module, when you are designing some product, you have to write everything in the programmed manner, right? In a Verilog, using a Verilog language, VHDL language. So here, when you're writing or else when you are using, if you want to specify only one delay format. So one delay format, this is how we can specify. Module is a keyword. Okay, we all know in the very first module we have discussed there are some keywords, lexical tokens, isn't it? Operators, keywords, and all. So here, coming to the keyword module, we are starting our program with the module keyword, and DES, description, is nothing but the name of the module that you are considering, and then this is nothing but the port list. So here port list, in this port list I am representing all the outputs first and then goes with the input. And then here this is nothing but the comments. Comment is also one of the lexical token that we have discussed along with the keywords. So in the comments we have discussed about the single line comment and the double line comment. So single line comments goes like this and the double line comments goes like this. This is the double line comments. So in the double line comments, there are legal and illegal comments as well. In between the comments, if you find anything like this, in between the statements, if you find anything like this, then it is nothing but the illegal comment. Okay. When you have such kind of comments, then it's nothing but the legal comment. So this is a module pertaining to one delay format, module, description, port list. And the statement says that here we are considering AND gate. Okay, so AND gate has two inputs, unit delay, two time unit gate delay. So as we are considering the AND gate, we have two inputs, right? So obviously we'll see the delay as 2 time unit gate delay. And then AND gate, we have 2 time unit gate delays, and it is a name of a gate. And this is nothing but the terminal list. This is a terminal list. And this is a name of a gate. And here it's a AND gate that you are considering. And here it is a delay. So we are saying that AND gate has 2 time unit gate delay. This is how I am representing. 2 time units. 2. If it is 10 time units of delay, this is how I can represent. So 2 time units of delay, name of the gate, and finally terminal list. In the terminal list, we are representing output delay and as well as output and as well as the input followed with the control signals if you have. Then see, buff if 0. Buff if 0 gate has 3 time unit delay gates. So here when you're considering a BufF 0, okay, BufF 0, BufF 1, these are the gates, they have input, output and as well as the control lines, right? So here regarding to this BufF, I can go for the 3 input delays, that is 3 delay format. Okay, so here BufF 0, and here how much of delay that I am considering? 3 delay, and B1 is my name of a gate, and the terminal is output and as well as goes with the input. And finally, I am ending up with the end module. So here, this is about the 1 delay format. So here only we see 1 delay, right? 2 and 3 are the 1 delay. So 2 is nothing but the 2 time unit of delay. 3 is nothing but the 3 time unit of delay for different cases. Coming to 2 delay format. So how can we write this 2 delay format? So same 2 delay format is module, description, the name of a module that you are considering, and this is the port list. And then finally here we are representing how a 2 delay format can be written. So we are considering the same gates and BufF 0. So for AND 0, the delays I have is 2 and 3. So these are the delays. As it is a 2 format delay, one delay I can name it as a rise delay, another delay I can name it as a false delay, isn't it? So for 2 delay format, we are representing with the 2 delays, that is 2 and 3. One delay, it could be of rise time, and another delay is false. That means what? Here, see, this is rise delay and this is false delay. So here the delay would be T of 2, and here the delay would be T of 3. So this is how the representation takes place for 2 delay format. And then BufF 0, for example, another. So for BufF 0, same. It is also I'm writing the format in the 2 delay format. So 4, 5 /4, 5 B1 output A and B, and finally end module. This is how I can represent 2 delay format. So 2 delays, 2 and 3 are the 2 delay points. One is with respect to rise time, another one is with respect to the false time. And this is a 1 delay format, so that here we can see only one number. The delay number, it would be represented with only one number. Coming to 3 delay format. So what does this 3 delay format says is same module, designing some module. In the port list, we are presenting input output ports. Coming to and BufF 0. So here we have considered 2 things, and as well as the BufF 0. So here and is 2 and 3, output 1. BufF I have considered 5, 6, 7. So this is nothing but the 3 format delay, isn't it? So BufF 0, 5, 6 and 7, B1 out A and B and module. So these are some specifications based on the delays. So we can specify, being a designer, we can specify the delays in terms of single delay format, two delay format and 3 delay format. So in 2 delay format, I can write like this, #2, 3. In 3 delay format, I can write 4, 5 and 6. So one of the, especially when it comes to 2 delay format, I can write 2 as rise time and false time. And coming to 3 delay format, even then here also I can write rise time, false time and turn of time, isn't it? So we have discussed what is a rise time. When the signal is switching from 0 to 1. So 0 to 1 is nothing but the rise time. And when the signal, it's taking its position from 1 to 0, it's falling down, right? Low, from high to low, then it is nothing but the false time. And what is this turn of time? Turn of time is when the signal is taking place beyond the limit numbers, beyond the limited space. If the signal is going beyond the limited space, then that value, it may go with respect to Z or with respect to X, that is high impedance value or the unknown value. Then such kind of delay is nothing but the turn of delay. Here in this turn of delay, we see the switch will goes off. Okay, whatever the switches that you are considering, though it is PMOS, NMOS and CMOS, whatever it is, whatever the switch that you are considering, make sure that, or else we will be observing that when it comes to the turn of delays, the switch goes to off in the turn of delay. Whereas here in the rise time, it goes from 0 to high, and in the falls time, 1 to 0. So these are the delays that we can observe when you are constructing, or else when you are designing some kind of module. Okay, though it is a complex module or a simple module, whatever the module that you are designing, and when it comes to the simulation part, you will be observing all such delays in the designing part. So this is about the time delays. So in the time delay switching primitives, we have many things to be discussed. In the coming class, we'll be discussed regarding the switch primitives of the time delays and so on. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.